All right. Ready for some more polar coordinates? Woohoo, yeah. All right, so we got through, if I remember correctly, and I'll do a quick review of this. We did inner loops. Go through the rules of that. We did cardioids, and I think we were just dabbling into dimpled limacons, but we'd only talked about dimpled limacons. Well, we hadn't really emphasized everything about dimpled limacons. So let me go and remind you about this. So we're on roughly 49. Okay, and also as a source, I want to show you, if you go to your, turn this on. If you go to page, is it 47 in the book? There's some great notes, everything you need to know about the graphs. This is back before I used to record. I had a kid, I think he had mono or something, and missed the whole week. And when he's coming back, he's like, man, so what's the book? The book was terrible. Like, I don't even know if it's in the book. It may be, because I just used these notes. But I went through and I thought, okay, what is every single thing they need to know about graphing, how to graph them, how to plot them, and I wrote it all up in one. And there's so great explanation if you're starting on page 47, if you get stuck on any of this. Okay, so just running through what we know already real quickly. We're gonna be looking at some different forms, but the ones we're going to talk about that are in the limacon family or the limacon family are the ones that have a sine function with nothing with the theta. Although we'll get to that. Nothing's with the theta. You got a coefficient with the either sine or cosine. It's either plus or minus there, and then there's a number out in front of that. So if I start taking away like the lead number, it's no longer a limacon. Okay, it turns rose curve or something else. So if it's in this form, I call this form like R equal A either plus or minus B and either sine or cosine of a single theta. If it's in that form, it's in this family. And the first thing to identify is the second number bigger? See, if the second number is bigger, then when you go A minus the B, you get a negative value. So if that's bigger than the first one, you get a negative value when you subtract the A minus B, and that indicates a loop, okay? And the length of that loop is just the negative value made positive. Okay, I think right here it says if I do B minus A, that's just kind of thinking the other way, and that would be the length of my loop. And then we said that lead number determines how wide it is. So you got to figure out what direction it's going. And it's going either what or what? Up or down? This negative one would be going down. So if I'm going down, how much? The total, 8. Right? We're ignoring the negative. The negative only controls direction. So if I'm going down 8 on this thing, that means I would go left and right. How much? The lead number. So down 8, left and right 3. Of course, there's going to be a value at the pole. The value at the pole is R can be 0. And the reason why you know R can be 0 is if sine was 3 over 5, a fraction between -1 and 1, which you know it can be. That's all it can be, right? Between -1 and 1. 3 minus that would be a 0. So it's possible to get a 0. Is it possible to get a 0 here? No, because sine 1, right? To make this go to 0, what can it be? Sine can only be between -1 and 1. Same with cosine. So with that in mind, right here it can be 0. That puts a little mark at the pole, which is like the origin. And then we said the length of in those two. But when this number's bigger, that's when you have a limacon with an inner loop. Okay? So anyway, all that's right here. Then you get to the next one we talked about. And there was a picture of this particular one. we talked about was a cardioid, right? And a cardioid is almost exactly like a limacon with an inner loop, except it doesn't have an inner loop. And how do you know that? Because if you were using the same rules you had before, what happens when you go 4 minus 4? Either way, you can literally think, oh, you can kind of say it's a cardioid with it's a limacon with an inner loop with a loop's length is 0, but that doesn't have a loop. So it changes its name to a cardioid because it kind of but the other rules are exactly the same. It still can have a maximum value of 8. It's going positive cosine, so it's going to the right 8. And if it's going to the right 8, it's going up or down what? 4. And is there a value at the pole? Yes, because that would mean the R value is 0. A length of 0 would be at the pole. And of course, I can go, if cosine's a -1, I get 4 minus 4 is 0. So it's totally possible to have that at the pole on a cardioid and a limacon with an inner loop. And a dip looks like that, not like this. It doesn't wave you through there like you're just kind of driving your car on a wavy road. It's almost like it dips, like you're parking it out the other side. Y'all seeing that? And I'll contrast that more now with the dimpled one. So the next one's the dimpled limacon. So that was the cardioid we just described. So the dimpled limacon, at the end of the day on Friday, a dimpled limacon says, well, in this case, if I go 4, and again, I'm not using that sign, I'm just thinking 4 minus 3, I get a positive value. Now, if I go 4 minus 3, the negative value is the length of the loop. Value here, and I know right here I'm thinking of it backwards, but I said if I take the B and subtract the A, I get a negative. But whatever, just stick with whatever rule you want. Bottom line is this number's bigger. Now, if this, and I haven't said this yet, but not twice as big. Okay? So if this is bigger, but not yet twice as big, then it's a dimpled limacon. Okay? So the same rules go for direction. Negative cosine, head left, 7, right? And if it's going 7 left, how much up and down is it going? 4. But does it hit the pole? No, it can't hit the pole. Why not? Because 4 minus 3 times something could only be 0 if cosine was bigger than 3, right? Because when I subtract 3, I still have a 1 left. But I can't make that equal to 4 or more unless cosine were like 4/3. That would give me 0. But why can't I make cosine 4/3? Because it's defined. So I can't do it, which means I can't hit the pole. So I can't dip at the pole. Now, the way I kind of see this or describe it is this. Like pretend, what's this, negative cosine? So on this graph right here, so right here, if right here, think of which would be a cardioid or a limacon with the inner loop. Think what would happen if I push this back. So think of it like a piece of spaghetti, wet spaghetti. I push this back, right, a little bit. It kind of flattens out my dip and makes a dimple, okay? So whenever you look at this, and this number's bigger, but not twice as big, the little dip part kind of flattens out a little bit and becomes what we call a dimple. And again, a dip is a going in there and reversing, as opposed to a dimple that kind of just curves through there. The difference? Because I'm going to look for that difference when I look at your work. But everything else is the same. Still going 7 left, up and down 4. The only difference is, sorry, I'm going left on this. So the dimple would be this way. All right, so I'm still going over there to 7. So it kind of looks like a cardioid. The only difference is it doesn't have a dip at the pole. It's got a dimple back there. Okay, how the difference between these? So if the difference is 1, go 1 back. If the difference is 3, go 1, 2, 3 back. Now, that right there is a dimpled limacon. Now, if the number, but it is twice as big or more, see, that's the dimple. See how it kind of rolls through there and it doesn't dip? So if it actually becomes twice as big or more, one, this is an example of a convex limacon. Okay, what happens is, again, think, if I keep pushing on that wet spaghetti noodle right here that's waving through there, eventually, if I keep pushing on it, it just goes, whoop, and it just pops. The dimple part goes away, and it goes from a concave looking thing, it pops out and becomes it doesn't really pop out, but I'm trying to give you a visual. It becomes a convex, right? So instead of having some concavity in there, it literally just pops out and becomes a convex situation. So that only occurs where there's no dimple, no dip at all. That occurs when this value still is bigger, but suddenly becomes twice as big or more. So the instant I hit 4, it switched. Like if it's 3.9, it may look convex, but it still has a slight dimple. But the second it hits, that value would become this graph would become a, and then any bigger than 4, it just remains convex forever. But again, the same rules hold. So positive sign, which way am I going? Up. How far up? 7. If it's going up 7, how much left and right? 5 left and right. And then because I'm going up 7 and left and right 5, and because there's no dimple, there's no way I can hit the pole. What's the only to be 0? Sign would have to be what for this to be 0? Think about it. I'd have to subtract 5, divide by 2. Sine of theta would have to be negative 2.5. Well, it can't be. It's only defined between negative 1 and 1. So there's no way for r to be 0 there at all. So if that's the case, it can't hit the pole. So how far back does it go if the graph is going up? Well, the difference. All right? So 5 minus 2 is 3. That means it would be down 3. And you can see that right here. 5 and 2 is 7, up 7. Because the lead number was 5. And if I subtract the 5 and the 2, I get 3. So 1, 2, 3. So I only have those 4 points. It does look sometimes very circular. And how would you know it's not a circle? I'll get back to that question. So you mark your 4 points right there, and then you remember, wait, I know there's not a dip because it's not at the pole. I know there's not a lead number. The A value was twice as big as the B value or more. So at this point, I just kind of round it off, and you're like a circle. I mean, try to keep it from looking like a diamond or an arrowhead or something like that, but try to make it look kind of circular. But honestly, I don't know that I've ever taken off unless somebody literally draws a quadrilateral on there. Then I'd probably dot you. But that would be it. So the more rounded you can be, the better. Really know that it's not a circle. Don't circles have to be in this form? Actually, these numbers right there, right? Plus bx plus cy plus d, I guess, if those numbers have to be the same, right? That would be a circle. Well, I could technically change this now that I know how to change from polar to rectangular, couldn't I? Couldn't I come in here and say, all right, this right is sine. And if you remember the clues I gave you for changing these, I said functions first, right? So sine is y over r. Then I said we never have fractions, so multiply 3 by r. And then at the last, as you're getting rid of fractions and getting rid of trig functions, if you should happen to have an r left that you can't get rid of, replace 5r. So at this point, I replace that with x squared plus y squared. I replace that r with the square root of. Now, does that look like a circle to you? It looks a little bit like one right here, but in order to get rid of that, what am I going to have to do? Square both sides? Maybe get rid of the 2y first, but now check it out. What happens when I square both sides here? What happens when I square both sides to that? It's going to be nasty. I'm going to have x to the 4. That's not a circle. A circle has x squared sorry, not x squared and x squared. Sorry, still Monday. So x squareds and y squareds, right? That's going to have x to the 4th and y to the 4th. And x squareds, y's, this is going to be a nightmare. I don't know. Well, I'll tell you what it is. It is a right? We just don't learn convex limacons in an ugly form like this. We just don't learn that. It's not important of polar graphs. You with me? So those are the main 4 functions in the limacon family. And I'm trying to catch up a little bit because I was a little bit behind. So I'm just kind of running through these notes. The next group, and you can see one there, and if you're looking at it, go, man, it really does look like a circle. It's not. There are circles that we'll talk about in a second. And you already are familiar with one circle. We've already graphed it. It was polar. What was it? We've done it already. Yeah, r equals something. Like if r equals 5, if the radius is 5, and it doesn't mention anything about the theta, so the theta could be anything, that gives you a circle at the origin. But there are also circles other places, right? And we're going to jump into that when we start dealing with rose curves. Because it's kind of a rose curve, but a special, basically a one-petaled rose curve. You'll see that right now. Okay, so I'm going to jump back to our notes. Okay, so right here, we've already talked about 1, 2, 3, and 4 now. We just didn't go through all of the examples. So I am on page 45, about midway down. Now, we're going to jump into a different kind of form, okay? Different about this r equals and this r equals than what we've already done so far. Well, there was always a number in front of the sine or the cosine. So there's nothing being added, or there's nothing like, there's no a plus b. Now there's no a plus b times, there's just an a times. So there's nothing added out front, or there's nothing that this is being subtracted from. What's the other change? Don't see it? The n with the theta. So I'm going to start multiplying that by a number. That might be multiplied by a 1, like in this case. Might be multiplied by a 2, might be multiplied by a 3. You need to learn what that number is doing, okay? These are called rose curves. So if you look at these and you see that it's in this form, a trig number theta, a trig number theta, a trig number theta. And cosines. And if you're like, what about tangent? What about cosecant? Yes, there are all kinds of other trigs that could give you different unique graphs. We're just not looking at them, right? It's pre-cal. It's not like pre-cal 10. I mean, you could keep going with math, right? I mean, we're just looking at the tip of the iceberg of math, believe it or not. Okay, so anyway, let's take a look at these. If you want to take your calculator out, you can, and go back to the polar graphs. So pull up my screen so you can see it. I've got my calculator in radian mode, and I'm just going to leave it all in radians because it keeps default. Every time I do a new graph, it defaults back to that 0 to 6.28 thing. So I'm going to blow this up a little bit, and I'm looking at 5 cosine theta. So 5 trig, put the number 1 in there, and then I'm going to put theta so that when I redo it, all I have to do. So right here, I'm just going to graph it initially, and you can see, bam, that actually is a circle. So when you have a rose curve that's in this form, but the n value is at 1, then you are going to have actually a circle. A one-petaled rose curve, okay? If I ask any 6-year-old in America, they're not going to go, looks like a one-petaled rose curve. They're going to say circle to this. Now, they might say circle to a convex limacon as well, but that actually is a circle. Let's call it a circle. And when it comes to graphing it, the little things that we do to graph these, you're going to see, you're going to have to do a little bit better than, because really all we do to graph these is mark that point and mark that point. But don't do this. They do this and then they label circle. I'm like, really? Okay, so if you're 2 points, which are endpoints of a diameter, go to the radius in the center, and if that's 2.5 each way, just eyeball 2.5, and then eyeball 2.5, right? And then do your best job at that point. But don't give me that little I don't know what it would be. Don't give me that when you're sketching. Try to do a little bit better. Y'all seeing this? Now, have you noticed it's still cosine? And cosine moves this way and this way, right? So, and we're not going to see a lot where you have a sine in the front, but if you really think about the math of it, tell me where is cosine maximized? Tell me, where is cosine its biggest value? Why? That's right. On the unit circle, if you think about it, 0, it's as big as it can get. So at 0 degrees or 0 radians, the biggest R value I can possibly get is when cosine is equal to 1. And cosine of 0 is 1, and 1 times 5 is 5. So sure enough, 5 to the right, 1, 2, 3, 4, 5 is as far away from the pole as I can possibly get. So I mark RB 0. Yeah, of course it can be 0. Why? Because cosine 0. When is cosine of theta 0? At 90? At 270? If you actually graph this in slow motion, it does this. This is like 45 degrees, 90 degrees. And then these are negative values of cosine. From this thing is like moving along right here. It's actually marking negative radii right here to there. And then from here, it's actually marking positive radii. And then the last, it's marking negative radii. Why? Think about the graph of the cosine curve. Positive values from 0 to 90, positive values. From 90 to 180, negative values. From 90 to 180, it's going negative values all the way through there. What about from here to here? More negative values. So like 181, negative, 182, which means it's just tracing over this again from 270 to 360, 270 to 360, positive. Awesome. Brought my charger for the Inspire. So if your battery's ever getting dead and you want to just take it and stick it in that and it locks in there and charge it up. You can leave it overnight or whatever. I mean, I can't vouch for its safety, but as long as your name's on it, I would think it'd be fine. Or if you just want to charge it for the hour you're in here, welcome to use that thing. So right here, chip. I want this. All right, so check this out. Mode, polar, where, zoom 6, zoom 5. Okay, so check out y equals r equals 5 cosine 1 theta. And now check it out. I'm going to go window to help us think. I'm going to go in 15 to. Okay. I'm going to have to do better than that. How about 5-degree increments? Sorry, how about negative 10, positive 10, negative 6. Okay, so check this out. Trace. I'm at 0 degrees. I'm at 0 degrees right now, okay? Now look what happens. Now I'm at, why is it doing this? Mode, degree, window, step. Okay, this is, ignore the X's and the Y's, and look at the theta. There's 5, 10, 10, 15, 20, 25, 30. These are all degree values. And by the time it hits 90, it's back at 0, right? And then from 90 to, think about unit circle, on the cosine from 90 to 180, it's negative. And look at this. As I move through there, look at the values. You can see I'm down. If I'm at, what's up here? Why is my value there? Negative R value. I wish it did better with the X's and Y. I don't know why it showed to do with the polar graph, but this is an old antique calculator basically. So you can see it all negative R values, but then when I hit 180, now it's rolling through all of these degrees, but you're going to still see it have negative values through all of those until it hits 270. And then at 270, you're going to see it come back up. Think about units, the graph up and starts having positive R values. Are y'all with me on this? So that's the graph of these with 1 theta. Okay, now what happens if I change it to 2 theta? Anybody got any guesses? You have more petals? Let's take a look. And this is going to throw you maybe a little bit. I'm going to change it to 2. I'm also going to make that 5, 6, make it a little bit bigger. Here we go. Ooh. Okay, so now I've got this thing called what we call a row. The thing that bothers a lot of people, they're like, well, if 1 has 1 petal, why does 2 have 4 petals? Well, let's keep looking. What would happen? And by the way, have you noticed where they are? 0, 90, 180, 270, 360, or whatever, right? So they're all the same amount of units apart. Okay, we'll log that in. And how long the petals are? How long are the petals? 6. Because the biggest cosine could be is 1, right? And if cosine can only be 1, 1 times 6 is the biggest possible length. So you're going 6 to the right, and then you're at 0 degrees, and then you're marking a bunch of other ones the same amount apart. All right, look what happens when I change it to 3. Anybody got a guess?
9. 3.
Check it out. 3. What? So 1 is 4. 3 is 3. Anybody got a guess on what might happen? But notice there's still 6 apart. I mean, 6 out. That's 6. Might not seem like it, but that's 6. Check it out. 1, 2, 3, 4, 5, 6. If you actually had a graph, 1, 2, 3, 4, 5, 6. If you actually had a real polar graph, can you see that it's 6 out? So there's still, and notice there, this actually, believe it or not, that's 0. This right here, 120, 360. See how they're all the same amount apart still? Anybody got a guess what's going to happen when I change it to a 4? If you haven't looked already. 8. Sure enough, 8. So why do the odd numbers only have odd numbers of petals? It's a trick question. They don't. I mean, they do. They actually have double the number of petals, but the second is located where? Overlapping. And you can see it on this calculator. You can't do this on yours because your calculator is so fast, it just goes and shows it to you. But this one is not as fast. The brain is not as big. So you can actually see it tracing. And watch, you can see it tracing even better if I slow it down. Where is it? Okay, check it out. I'm going to slow it down to 2. Yes. You can do this. You can put this little, no, not there. You can put this little, that. Okay, check this out. So you can see on this one where there's 8 petals, you can clearly see it graphing all 8 petals, right? And you might have a fancy pattern. It's literally going from 0 to 360. 0 degrees, I'm here, and then 1, 2, 3, 4, and then it's marking negative R values. But it's literally rotating degrees and angles through here, rotating more degrees and angles through here, rotating more degrees and angles through here, more degrees and angles through here. It's literally rotating through them. But check it out. I'm going to change it to 5, and I'm guessing you're going to say there's 5 petals, right? Say on the test, because that's what you see, but check it out. So here are your 5, and then like it's just tracing over them again. So the reality of it is, no matter what the number with theta is, you technically could double it, and that's how many times you're hitting a petal. But with the odd numbers, you don't see them. So with the odd numbers, we say petals. But with the even numbers, we say we have double the number of petals. Now, where are they located? Have you noticed a common petal with all of these? At 0 degrees. At 0 degrees, no matter what is cosine? Cosine of 0 degrees is what? Does that change? This is a big deal right here. Does that change whether I have 0 or cosine of 2 times 0 or cosine of 5 times 0? No matter what is it?
1.
It's equal to 1. So if I end up having r equals 6 or whatever on all of these, if this is always equal to 1, then I'm always going to have 6 units out pointing at 0 degrees. Are y'all seeing that? Well, that means if it's a cosine rose curve, you can always start by marking a petal at 0 degrees or 0 radians, depending on how you're thinking about it. Well, I like to think in degrees. Now, how many petals does it have? Well, if you know that there's a 5 right here, like we just did this graph. If you know there's a 5, 1, 2, 3, 4, actually this was a 6. Sorry. Yeah, 1, 2, 3, 4, 5, 6. Theta. So you know that you can mark one out there 6 units out, and then if there are 5 petals and they're always equally spaced, how many degrees do you put between each one? How do you find that? How do you figure out how many degrees are between each one if they're all spaced evenly? 360 divided by 5. And when I divide 5 into 360, it goes 72 times. So I'm going to come up here and mark 72 degrees. Add another 72, 144. Add another 72, to what, 16? Add another 72, 288. Add another 72, 360. And I just look, and you'll be given a much better graph. Your graph will look like the ones that are on your sheet with a line, so it's easier to go out 7. Each on your graphs that you see on your paper, each one is separated 15 degrees apart. So you might look up here and go, well, it's hard to tell because this is a 30 and that's a 60. That's right, but in the middle it's 15 between 60 and 90, so it's 75. So you would just go a little bit inside that and then go up. So you should be able to do that pretty easily, I think, if you're just a little careful. And then you mark them all, and then you're like, well, how fat are the petals? You notice the more petals I get, the skinnier they've gotten, right? If you do something like y equals 10, you're going to have a, whoa.
It was 1.
Oh, 1 theta. Sorry, 10 theta. If you do something like this, that's 2. And the reason why it's not pretty here is my step is not small enough. But you can see I've got a whole bunch of petals. If I really want it to look better, I make a better step. You don't have to worry about this on yours. But the smaller I make the step, the slower it takes. But you can see right here, I get really, really skinny petals here composed to when there's a 3, there are a lot fatter petals. Do the best you can. But one thing I do want you to pay attention to, and that's this. If you're sketching theta, okay? If I'm sketching this, I'm going to turn this off for a second. So I'm sketching 6 cosine 3 theta. You know you're going to be going, all right, 1, 2, 3, 4, 5, 6. And if there's a 3 theta, how many degrees are between each petal if that's a 3? 120. So you're going to look up there and go, all right, 120. And again, if that's 45, 20. So I'm going to go out 1, 2, 3, 4, 5, 6. Again, this should be easier for you. You're going to be like right there maybe, and then you're going to be 1, 2, 3, 4, 5. You're going to have the graph. You're going to be maybe right there, and you're like, okay, and you're going to, of course, be at the pole because they always cross through at the pole, and you're going to go, well, how fat do I draw them? As long as they don't overlap each other. As long as you're, see, I have that overlap in there like a Venn diagram. It doesn't do that. So right here, as long as they don't overlap, you're good. So if you want to sketch on the skinny side, this is maybe on the skinny side. Great, but you just don't want any overlap because it doesn't do that. Now it probably is a little fatter, is my guess, right here. But if I go back and sketch it, it's good enough for government work. Pretty spot on. So right there, but the bigger the value with that, the skinnier the petals are going to get. But as long as they don't overlap like this, you're okay. Y'all with me? Now this is cosine, and the great thing about cosine is cosine. It doesn't matter whether that's a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm always going to have a petal. 0, figure out how many petals based on that number. If it's odd, you have that many. If it's even, remember to double it before you divide it into 360 because you're spacing out twice as many, but not with sine. Check out sine. Changing it to sine. So I'm going to start with 1. What do you think is happening here? It's going to be a circle. Back to what we said before. How long is the radius of the circle? 6. Right, it's going to be 6. Where would sine be equal to 1? At 90 degrees. So at 90 degrees, sine is 1, 1 times 6. So this thing should be going straight up, right? And it is. And you have a circle going straight up. Not a one-petaled rose curve, but an actual circle. Now, here's where it starts getting tricky. I want you to think about this. Right here, this is what we have. R of n theta. Now the problem now is, what if I change it to a 2? The first thing that's going to happen is what? I'm not having 1 petal, I have 4 because it's even, right? But check it out. One of the petals is not at 0. And why is that? Because check this out. Cosine is equal to 1 when? When what? When this is 0. And this is 0 always when theta is 0. Doesn't matter what 3 is. Ever, does it? It could be, it doesn't matter what the n is. Could be 3, could be 5, could be 7, could be 10. If theta is 0, the whole thing's 0, cosine of 0 is 1. But wait, and when cosine is 1, it's but wait, when is sine maximized? Sine is maximized at 1 when this is 90. Well, that's different because n theta is 90 when n is 1. That's going to equal 90 when theta is 90. But when n is 2, when is this going to be 90? Theta is 45. When n is 3, when is theta going to be 90? When is that going to be 90? When angle is 30. So you have to find the first petal. Like on this one, I'm not going to have a petal. So can I change it to 2? I'm not going to have a petal straight up. Check it out. My petal, I'm going to have one at 45 degrees. That's 45. I know that because petals, or the tip of the petal, that's where R is maximized, at the tip of the petal. And R is maximized with sine when the whole 2 theta is 90. And the theta, therefore, changes. It depends on the number up front. Cosine didn't act that way. Cosine, the n theta is 0. And that's always when theta is 0. So literally, on these, I'm not going to ever have a common petal. And by the way, these do touch at the pole. I know on top of the axis, but these are going back. If I took the axes off, you'd see it go right through there. All right, that's how I know people cheat on a test. Every now I'll have somebody, and they'll trace it, and they'll be like, because you don't have a calculator on your test. And I can tell some suckers like got a calculator under their desk, taking a look at it. It shouldn't be a big deal. These aren't tough to grab it. They don't do that. They come all the way through the pole right here. Okay? So tell me, and by the way, once you find the first pedal is right up here at 45 degrees. Pedals. So this pedal, 4 into 360 is 90. So from there, add 90, add 90, add 90, and then sketch your pedals. And notice they don't ever overlap. Let's do another one for the values. What if I put a 3 on there? I got 3 pedals. Where's the first one? Not at 90. 3 theta into 90 gives me 30. So my first pedal is going to be at 30 degrees. Right here. I mean, if there's 3, how many degrees apart are they? 120, add 120 to 30, and you get 150. Add 120 to 150, you get 270. Are you seeing these? Now, guys, we have talked about all the rose curves, but there are some other ones we're going to have to get to tomorrow. Because that's where I start throwing you curveballs. So we're just a little bit behind. That's all right. We'll make it more. Hey, guys, the first review on polar is what you're doing tonight. Do everything you can. There are a couple, if you see any graphs that say R squared or that have 2 pedals, you think about it, how do I do 2 pedals? Can't put a 2, that makes it 4. If you see those, we haven't gotten to those yet. Those are called lemniscates. But if you want to read up on them, I do have some notes on lemniscates. Right. See you guys.